Good day everyone and welcome to our webinar on 5G R&D with NetSim, Advanced Modeling and Analysis Features. I am Pranav Vishwanathan and I am joined by my colleague Kanakaraj Krishnamurthy. Over the next 45 minutes, we'll be exploring the advanced modeling and analysis features that NetSim offers to enhance our users' 5G R&D. We have an exciting session ahead, so let's get started. Let me walk you through the agenda of this webinar. First up, we have two tools, the Rapid Scenario Generator and the Rapid Application Configurator. These tools will help us quickly generate scenarios and configure applications. Next, we have log files that we will be using for radio measurements and radio resource allocation. These files will be useful for deep analysis. We will then talk about our new Excel-based mobility file used to model the mobility of UEs. Moving on to the more technical aspects, we will discuss code block segmentation, which is an important 5-layer abstraction to model 5G data transmission in NetSim. We will then look at how NetSim simulates hybrid automatic repeat request or HARQ with soft combining, an error correction technique used in 5G. We then delve into NetSim's block error rate, that is BLER, and outer loop link adaptation or OLLA. Next up, we look at NetSim's uplink interference model. Then we'll talk about a new band, the 60 GHz N263 band, a new addition to NetSim. Lastly, we have the handover modeling, which now has parameters such as handover margin or hysteresis, time to trigger, and handover interruption time. Finally, we'll be discussing our future roadmap plan for the next version of NetSim. We'll end with a Q&A session. So now we have a rapid scenario generator in NetSim that allows users to quickly create scenarios with a large number of GNodeBs and UEs. Let us look at a brief demo. You will notice that the rapid scenario generator is already open and ready for use. At the top of the interface, you have the option to set the environment size for your simulation. There are input fields provided to specify the number of GNodeBs or base stations and the number of UEs within your network. Additionally, you can select various placement strategies for GNodeBs and UEs, such as random, uniform, or file-based placement. The default configurations for GNodeBs and UEs can be used, or you can input custom settings using a reference configuration file. For this example, we will create a scenario featuring 20 GNodeBs and 500 UEs, with both types of devices placed randomly within the simulation environment. The scenario is now generated in NetSim and you can observe the following. Red triangles represent GNodeBs. Green circles denote UEs, and blue diamonds on the right signify the core network devices. Similarly, users can also configure traffic flows within the scenario. The Rapid Scenario Generator is a powerful tool that can save time and effort when creating complex scenarios. NetSim's UI now provides a convenient way for users to enable protocol-specific log files using the Logs option. I now open a pre-saved 5G scenario in NetSim. Next, I click on the log files in the ribbon and you can see the list of applicable logs available for 5G. Before running a simulation, users can choose the desired log files they want to generate. After simulation, they can access the log files from the results dashboard and analyze them in detail. I enable radio measurements and radio resource allocation log files. Then I run the simulation. Post-simulation, you can see that the log file can be opened from the left bottom panel in the results window. These log files are beneficial for users who want to fine-tune network parameters and optimize performance. By drilling down deep into the log files, users can gain insights into the behavior of network protocols and identify areas for improvement. Let us now look at the radio measurements and radio resource allocation or PRB allocation files in some depth. First, I open an existing radio measurements file from the results dashboard. The format is .csv and the file can be opened in Excel. .5G radio measurements log file records UE ID, UEG node beat distance, then the channel, then path loss, shadow fading loss, received power SNR, interference power, beamforming gain, SINR and MCS. The log has separate entries for downlink channel PDSCH, uplink channel PUSCH, and control channel PBSCH. For each G node B UE pair, for each carrier and for each MIMO layer. Next, I open the PRB allocation log. You can see the slot ID, G node B ID, carrier ID, available PRBs, UE ID, and the bits per PRB. Next, as you may already know, NetSim's mobility modeling allows users to simulate the movement of UEs in the network. In this example 5G scenario, I right-click and open UE properties. Under mobility, I open file-based mobility. You can see that we now have CSV file support. Users can configure a specific movement trajectory by providing the appropriate coordinates for the devices in a CSV file. What makes this powerful is the convenience it offers in using Excel's features to set the input values. Let's say I want the UE to go from the left to the right. I set the initial two coordinates in Excel and then use the drag and pull functionality to simply generate the rest. You can now see how it saves time and effort in configuring your simulation. We will now explore a newly added feature called code block segmentation, which is an important file layer abstraction. This and the next two slides are slightly technical, and we'll do our best to explain the concepts in simple terms. Let us now understand code block segmentation with an example. Consider an application layer packet of size 1460 bytes. After addition of UDP, IP, SDAP, PDCP and RLC header, the size of the packet when it enters the MAC is 1506 bytes. At this point, the MAC scheduler allocates physical resource blocks or PRBs based on the available bandwidth and the scheduling algorithm. The transport block size is then calculated using the allocated PRBs and the chosen MCS. The calculation is explained in the table. We have considered the 3.5 GHz band with 40 MHz bandwidth and a subcarrier spacing of 15 kHz. The MCS is 17 and the traffic generated is full buffer. Based on these parameters, the total PRB count is 216, and this gives us a transport block size of 130,240 bits. For a TB of this size, we get 10 full RLC SDUs of size 1560 bytes and one RLC SDU of size 1220 bytes. With this background, we now turn to code block segmentation in the file. This slide is somewhat complex, and let me simplify it for you. First, in 5G NR, data sent over the network is divided into smaller pieces called code blocks. The size of these code blocks depend on the type of LDPC base graph used. Secondly, if the transport block exceeds a threshold, the transport block is divided into multiple code blocks of equal size. The threshold is different for each LDPC base graph. For LDPC base graph 1, the threshold is 8448, while for base graph 2, it is 3840. Thirdly, if a transport block is larger than 3824, an additional 16-bit or 24-bit CRC is added at the end of the TB. If a TB is segmented into code blocks, each code block has an additional 24-bit CRC added at the end. Fourthly, the number of code blocks in a code block group can be set by the user in NetSim and can range from 2 to 8. Lastly, the flow diagram helps determine the code block size. The variables used in the formula are L for the extra CRC bits, C for the number of code blocks, TBS for the size of the transport block, and K prime for the number of information bits in the code block. The base matrix expansion factor ZC is calculated by finding the minimum ZC in all sets of lifting size tables such that KB times ZC is greater than or equal to K, where KB represents the number of information bit columns for lifting size ZC. Now let us look at how a packet is transmitted through the file layer. For this MAC TB size and code rate, per the tables, LDPC base graph 1 is selected. Since the TB is larger than the KCB threshold, the code block size is 8448 bytes. And the number of code blocks is 130,240 divided by 8448 minus 24, which comes to 15.46. This means we need to transmit 16 code blocks. An additional 24-bit CRC is added at the end of each code block, bringing the total CB size to 8478. The number of code blocks per code block group is set to 8, which means that 16 code blocks are aggregated into 2 code block groups and transmitted over the air. The resulting size of each CBG is 130,624 bits, and the number of information bits in each CB is 8168 bits. Thus, we see that the packets are first grouped into a transport block. The transport block is then split into code blocks. The code blocks are grouped into code block groups. It is the code block groups that are transmitted over the air. This is an important part of the 5GNR PHY abstraction in NetSim. Next, the hybrid ARQ protocol, or HARQ, is the primary way of handling retransmissions in 5G. This technique involves a combination of retransmissions and soft combining. In the 5G system, packets are transmitted as code block groups over the air, and the receiver sends an acknowledgement or ACK message if a CBG is received successfully. If a CBG is in error, a non-acknowledgement or NACK message is sent. The transmitter sends the next CBG if it receives an ACK message, and it retransmits the last transmitted CBG if it receives a NACK message. In traditional HARQ technique, CBGs marked as errors are discarded. However, in 5G, the errored CBGs are stored in the receiver and combined with the retransmitted CBG. NetSim uses HARQ with soft combining in both the DL and in the UL and supports up to a max of 16 HARQ processes. I will now show you the CBG and HARQ properties in NetSim. Right-click and go to the GNodeB properties. In the data link layer, you will see 4 HARQ parameters. HARQ mode to enable or disable HARQ. The number of HARQ processes with a maximum of 16. The number of code block groups per transport block. And the HARQ retry limit with a maximum of 4. All these parameter values are as per standards. Moving on to BLER. Users can now set a specific block error rate or BLER target in NetSim 5G simulations. Right-click on GNodeB properties. You can see the MCS, BLER, and link adaptation parameters. The first factor decides how the initial MCS selection is done, whether Shannon theorem based or after using an attenuation factor. The second parameter allows users to enable or disable BLER, and then users can enable link adaptation algorithms and set a target BLER. Once this is set, NetSim determines BLER from SINR BLER data tables. NetSim has exhaustive SINR BLER data for various transport block sizes, for all modulation and coding schemes, for 2 base graphs, that is base graph 1 and base graph 2, and for all 3 tables, that is table 1, 2 and 3. The SINR BLER data was generated through an in-house proprietary link level simulation program, and the results have been validated against published literature. The outer loop link adaptation or OLLA feature in NetSim is responsible for making necessary adjustments to the MCS to maintain the average BLER equal to the target set by the user. Let's look at OLLA in some depth. A rate adaptation in NetSim is in 2 parts. Let's look at the figures. On the left is the inner loop adaptation based on the SINR The UE sends back the CQI to the G node B based on the SINR it receives in the downlink. Based on the CQI, the G node B adapts its MCS. On the right is the outer loop link adaptation algorithm. This is used at the base station to make further adjustments to the MCS based on the inner loop algorithm. As you can see, the inner loop algorithm only uses SINR and doesn't take into account phi errors. Here is where OLLA comes in. OLLA adjusts the modulation and coding scheme to maintain the average BLER equal to the target set by the user. We explain this working in the next slide. OLLA is a feedback loop technique used in NetSim to adjust the instantaneous SINR value by adding or subtracting an offset based on whether a positive or negative HARQ ACK, that is, whether an ACK or a NAC is received, such that the average block error rate converges to the target BLER. The OLLA compensation equations and its relation to the BLER target is shown. Users interested in knowing more can check our online documentation or write to us. Let us look at the two plots from NetSim. In the top plot, the target BLER is set to 0.1, which means that the algorithm adjusts the SNR compensation to maintain an average BLER of 0.1. Similarly, in the bottom plot, the target BLER is set to 0.2, and the SINR is compensated to track the 0.2 BLER target. Now we turn to interference. NetSim utilizes interference over thermal, or IoT, to model uplink interference in 5G. This figure explains UL interference. UE1 is sending data in the uplink to BS1, while at the same time other UEs are sending data in their uplink to their respective base stations. The signals from the other UEs interferes with the signal from UE1. This happens at base station 1, which receives all the signals. We will now look at how UL interference can be configured in NetSim. Again, go to the G node B properties, and in 5G RAN under the file layer you can see the interference model setting for DL and UL interference. Under UL interference, users can set interference over thermal and configure the IoT value in dB. One remark for participants who understand interference well: note that unlike DL interference, NetSim does not model UL interference based on geometry, but rather allows the user to set a value of interference over thermal. This is because we can't make the full buffer assumption in the UL. The N263 band is a recent addition to NetSim. This band is mainly used for outdoor fixed wireless access, or FWA, and small cell deployments, delivering high data transfer rates. It is important to note that this is a high frequency band, and this also means that the band would have much higher propagation losses, which NetSim models per the 3GPP standards. Apart from that, to facilitate the modeling of oxygen absorption and rain attenuation in the N263 band, NetSim has an inbuilt interface with MATLAB. You can see this here. Let us look at the N263 band in the G node B properties. We select N263 under CA configuration. The numerologies configurable are 3, 5 and 6. This means that the subcarrier spacing supported is 120, 240 and 960 kHz. Under numerology 6, we can see the bandwidth supported are 400, 800, 1600 and 2000 MHz. We have now included 3 new parameters for modeling handovers in 5G. We go to the GNodeB properties, and in the data link layer under handover parameters we can see handover interruption time, handover margin and time to trigger. Handover interruption time is the time for which service is interrupted during a handover, and this can be configured by the user in the UI. This variable would affect the end-to-end delay and throughput during the handover process. Handover margin, another UI variable, allows the user to set an SNR margin for handover decisions. In NetSim, handover is triggered when the signal strength from the target cell is offset higher than the signal strength from the serving cell. This offset value is 3 dB. This parameter can help avoid ping-pong handovers. Time to trigger is a new UI variable that specifies when a handover event should be triggered. With TTT added, a handover event is only triggered if the handover condition, that is, difference in the SNR between the target and serving cells is offset higher, holds true for a duration equal to TTT. The user can adjust this parameter to optimize the handover process based on the network environment and UE capabilities. Coming back to the presentation, let me explain the figure. Consider a case where a UE is moving from GNodeB 1 to GNodeB 2, where the channel is time varying. The GNB 1 SNR is shown in black and the GNB 2 SNR is shown in blue. Instant when SNR from GNB 2 is greater than SNR from GNB 1 by delta, which is the handover margin, event A3 starts. At this moment, time to trigger also starts. Once time to trigger ends, the handover procedure and control packet exchanges are done. After that gap, the handover interruption time takes effect. During this period, the UE is not connected to either GNodeB. Post this, the UE gets associated with GNodeB 2. In this final slide, I present to you a product roadmap for NetSim v14. That is the next release. The first feature we are working on is network slicing for EMBB use cases. This will allow us to provide rate guarantees by dynamically assigning resources. Next, we are looking at non-terrestrial networks, which covers low Earth orbit or LEO satellite constellations, as well as modeling Earth satellite links and inter-satellite links. Then we are exploring multi-access edge compute or MEC, which brings compute at the network edge rather than at remote servers located in far-off data centers. This is particularly useful for URLLC applications like industrial IoT and autonomous vehicles. Finally, we are looking at machine learning for 5G, which includes the generation of synthetic data for training ML algorithms, as well as interfacing for RL algorithms such as multi-armed bandits, Markov decision process, and Q-learning. We are also providing interfaces for DNNs, that is deep neural networks, recurrent neural networks, generative adversarial neural networks, and other types of neural networks. We have now come to the end of this webinar, and we will have a Q&A session.